If you watched the previous video, I derived the formula for time dilation, right? And that formula was that the dilated time, or the bigger time, right? That the moving clock ran slower, and that if we took the not moving time, or the proper time of the clock, and divided it by the square root of 1 minus v squared over c squared, okay, we got the dilated time. This factor here is a factor that is, as v increases, gets less and less. It starts off as 1. If this is 0, 1 minus 0 is 1, and the square root of 1 is still 1. So the dilated time is the same as the proper time. If it's not moving, right, it doesn't dilate. As we approach the speed of light, of course, this square root approaches 0, and 1 over the square root approaches infinity. So here's a graph of that. And we talk about that thing as we call it the Lorentz function, and that's or Lorentz factor. And that's something that's in the data packet. I think it's confusing to write it that way, and I don't tend to use that, but just a heads up, right? If you graph the Lorentz factor, you'll notice that at half the speed of light, there's really only a small difference between a classical calculation and a relativistic one. At about 0.2 of the speed of light, it's essentially the same. You can't tell on this graph. So that's sort of a rule of thumb. About 0.2 the speed of light, you can, or a tenth the speed of light. And the speed of light is, of course, in meters per second, is 3.00 times 10 to the 8th meters per second, right? So as long as you're going slower than 3 times 10 to the 7th meters per second, you don't need to worry about this stuff, okay? Now, here's the deal with these other things. Not only does time, a moving clock, run slower, okay, a moving object, a moving clock will actually, if it's a round clock, it'll actually appear oval, okay? So the length in the direction that you're moving actually contracts. This is called length contraction. It only happens to the direction, the dimension that's parallel to the direction of motion. So here's a picture of me sitting still. If you move that thing at about, I don't know, 0.8 the speed of light, this is what it would look like. It would shrink. I'd look tall and thin like that, right? Here's the formula for it, and notice that that little square root of 1 minus v squared over c squared that gets less than 1 is now multiplied by the original length. So this is the proper length. Proper in this case means it's not moving with respect to us, and this is the contracted length, or moving length. Okay, they shrink, they contract. This is called length contraction. Okay, now here's a cool thing about this. I don't know if you recall, but this thing actually reconciles our that whole idea, right? We're talking about how if you stood in front of this car, let's say this thing is moving toward us, right? Let's have it move at 0.866 the speed of light. That's what we mean by this, right? Okay. If they're doing that, let's say they're moving that fast. Here's this photon. That's a photon from their headlights, right? They see that photon moving with respect to them at fully the speed of light. We see, of course, that photon that came from them as going the speed of light. We see them going just a little bit slower than it, right? We see them going just a little bit slower than that photon. 86.6% as fast as that photon. And the question is, how can we see that and how can they see that? Remember that their frame of reference is really like this. It's been contracted. The car, the wheels are no longer round. Okay, the photon, which was that shape, now is like this shape. Everything's been shrunken in this direction, right? Okay, so it's a bit like those tents in Harry Potter where you get inside of them and they're quite large, but from the outside the dimension is, or the frame of reference is quite small. Okay, in a very small contracted frame of reference, you can have large velocities that are not perceived by us outside that frame of reference. So I don't know, that's kind of a cool thing, right? And then the other thing that happens is that masses dilate. Okay, dilate means to get bigger. Okay, so the summary is that time, right, moving clocks, time runs slower. Lengths get shorter, right? And mass dilates, mass gets more. Now this makes sense because remember, energy has mass, right? And so something that gains energy is going to gain mass simply because it gained energy. E equals mc squared, right? Right, this means that it's going to gain an amount of mass. The change in mass is going to be E divided by c squared, okay? So one cool thing is that we can look at the an electron here, right? If it's at rest, if we convert its rest mass, it's 9.11 times 10 to the minus 31st kilograms. If we turned that all into energy, converted that to electron volts, it would be about 500,000 electron volts. Okay. If we now accelerate the electron through 1,000,000 volts, it now has 1,000,000 electron volts of energy. Its new mass is 1 MeV of energy plus 500,000 electron volts of rest energy, right? The energy represented by its matter, right? Using E equals mc squared, right? Its new mass is this, right? You know, the Large Hadron Collider gives protons something like 7 teravolts of energy or something like that, right? It's just a crazy amount of energy. So moving objects gain mass. Here's the formula for it, right? It's just like time, right? We put the mass in there and it's 1 minus v squared over c squared. So the mass will dilate because this number here gets less than 1. And this is, of course, energy mass that we've gained. Okay, so that's the summary, right? If we need a summary for this, okay, let's do the summary. Clocks run slower. So moving, wow, my pen is really bad. Moving clocks run slower. Okay, length gets shorter, right? And mass increases. And we use this factor. We use this factor we use that factor to make clocks run slower, length get shorter, and make mass increase. It's all this factor here. Or if you want to use the thing in the data packet, they say 1 over that factor. It doesn't matter. We'll just do math. Okay? I'm going to do a couple examples here, and you should watch those. You should probably do a lot of these examples. That's the only way really you're going to learn how to do these.